Okay guys, right now we're going to be solving quiz number 3, version A. This was given in class on Friday, March 1st. The first question is to ask us to write the dual of an LP. In order to do that, the dual of a minimized problem is a maximized problem. It's always the easiest part. Then we know there's going to be a decision variable in the dual associated with each constraint in the primal. So in other words, we're going to have two decision variables. We'll call them y1 and y2. The coefficients in the objective function of the dual are going to be found by looking in the right-hand sides of the constraints in the primal. In other words, my dual objective function will be maximized 5y1 plus 2y2. Okay. The next thing I will do is start to write out my constraints. Since there was two decision variables in the primal, I know there's going to be two constraints in the dual. And the right-hand sides of those constraints in the dual will be found by looking in the coefficients of the objective function for the primal. Okay? In other words, I'm going to have a first constraint with the right-hand side of 1. Second constraint would be right-hand side of -1. Okay? The next thing I do is try to determine the types of these constraints for the dual. The types of constraints in the dual are determined by the types of decision variables in the primal. So in the primal we have two decision variables. Both of them are non-negative, which we said are normal decision variables. This means in my dual I'm going to have normal constraints, which for a maximized problem are less than or equal to constraints. Okay. To write out the A matrix for my dual, I simply need to write out A transpose for my primal. So in other words, my first row in my dual would be found by looking at the first column in my primal. So I've got y1 plus y2. The second row in my dual A matrix will be found by looking in the the second column of the A matrix in the primal. So I'll have 0 right here, and then I'll have 2y2. Okay. Now the only thing left to determine is what are the types of decision variables in the dual. In other words, I've got y1, which will have some relationship with 0, and the same for y2. The types of decision variables in the dual will be determined by looking at the types of constraints in the primal. So in other words, y1 was associated with this constraint, which was a less than or equal to constraint. A less than or equal to constraint for a minimized problem is a non-normal or an opposite type constraint. And an opposite type constraint in the primal will be associated with an opposite type decision variable in the dual. We said an opposite type decision variable is always less than or equal to 0. The second decision variable in the dual, y2, is associated with the second constraint in the primal, which is an equal to constraint. Okay? Whether the problem is a min or a max, we said that equal to constraints are associated with unrestricted and signed decision variables. In other words, y2 could be greater than 0, equal to 0, less than 0. It's not restricted, so we write it like that. And now you're done writing out the dual. Moving on to the second problem, the problem statement says that an LP's current optimal solution is at the extreme point, or the basic feasible solution, determined by the intersection of these two constraints. And it asks you to determine the range on which a right-hand side value, particularly B1, or the right-hand side of the first constraint, can vary and this basis remain optimal. Actually, this wasn't intended to be too hard. Basically, you just needed to remember what we said in class, that when we have an optimal basis for an LP and we want to vary a right-hand side, that basis will remain optimal as long as the basis remains feasible. So essentially the idea was this. We're going to be varying the right-hand side of constraint 1. So in order to sort of investigate that, we're going to add a delta right there. And we just need to solve for x1 and x2 in terms of delta. So I'm going to write 3x1 plus 2x2 equal 19 plus delta. And then I'm going to multiply the second constraint by 2 on both sides so I can solve a little easier. It's just going to be 2x1 minus 2x2 equals 6. Add those two constraints, you'd get that 5x1 is equal to 25 plus delta, or x1 is equal to 5 plus delta over 5. Okay? Plug that value for x1 into the second constraint, and you can quickly get that x2 is equal to, well, let me write it. If the second constraint just says that x2 is equal to x1 minus 3, if we substitute in what we just found for x1, we'd get that x2 is equal to 2 plus delta over 5. Okay? So we've solved for x1 and x2 in terms of delta. Now we need to determine what values delta can take in order for these two variables, x1 and x2, to remain feasible. Okay? Now I made the comment in class, we assume that x1 and x2 are non-negative decision variables, but if you'd made some other assumption, you could have clearly stated that and solved the problem based on that assumption. But we'll go on this assumption that x1 and x2 have to be greater than or equal to 0. So if x1 is equal to 5 plus delta, what values can delta take for x1 to remain positive? Essentially, this would have said that delta needs to be greater than negative 25. Okay? The second thing we found is that x2 is equal to 2 plus delta over 5. What values does that tell us delta can take in order for x2 to remain feasible? Delta needs to be greater than negative 10. Okay? Now we found two pieces of information about what values delta can take in order for the solution to remain feasible. If delta has to be greater than greater than negative 10, and delta has to be greater than negative 25, putting those two pieces of information together, you'll just wind up saying that delta has to be greater than negative 10. Okay? Now, again, what was delta here representing? Delta was representing the change in the right-hand side of the first constraint. And the question asks to determine the range on which that right-hand side, or B1, can vary. So if we just translate this change, delta, back into B1, we would have said B1 can be in 9, B1 should be at least 9, in other words. You could have also said B1 has to be greater than or equal to 9. Okay? And that's how sensitivity analysis can tell us what values B1 can take and this basis remain optimal.